to give a talk and being such a gracious host. Actually, I'm not going to talk about the title, since it turns out there's a interesting mistake in what the work I've been doing with Chen-Yang Xiu and Christopher Haken. So I should say, maybe I should start with saying that this is joint work with Christopher Haken, Chen-Yang Xiu. So, you know, what I'll do is talk about a series of interesting conjectures. Okay, so let me start by mentioning two seemingly completely unrelated problems. So I'll put one on this side, one on that, one on that side. They're both, well, one of them is very, very classical. Everybody knows. So if you take C, a smooth curve, genus at least 2, then there's an upper bound on the orthomorphism group. So everybody knows that, and I'll go through a derivation of that fact, which is sort of related to why I'm interested in high dimensions. But before I do that, let me mention the other problem. So suppose I take a germ of a holomorphic function from Cn to C. So I've just got Cn to C holomorphic, but as I say, it's just a germ. And what I'm interested in is I want to measure the order of vanishing of f at the origin. Okay, so one thing I could do is I could take a power series expansion for f and just look at the multiplicity. And that's an interesting invariant, but I want something that's slightly more subtle than that. So what I could do is I could sort of, instead of, so I say order of vanishing, because it's going to be something a little bit more subtle than the usual one. So I could look at the order of the pole of 1 over f. In particular, I could ask, is 1 over f, or let's say, let's get a real valued function, this guy, integrable? Well, so locally integrable. And so I can sort of just change that, make that L2, so is 1 over f squared integrable. And in fact, actually, what I could do is even slightly more interesting. I could look at the largest, or the supreme, I guess the supremum of t, so a real number such that 1 over f to the 2t is integrable. So let me give you an example of this to give you an idea of what's going on. So very easy example. Let's suppose I took from C to C, just Z goes to Z. Okay, so I am looking at 1 over Z to the 2t, and I'm asking if that's integrable. So I'm looking at this integral. Okay, I don't dx dy. So this morning, at first I didn't get an internet connection, and I couldn't remember how to change polar coordinates to Cartesian coordinates to polar coordinates. But fortunately, there was an internet connection, and then yeah, exactly. You know, as we all know, there's nothing. There's never any problem with Wikipedia. So, so of course, z squared is like x squared plus y squared of x and y, the real parts. So this is r squared. So then 2t, and then Wikipedia says there's a factor of r. So So I'm asking, so in other words, what I'm really interested in is I mean, obviously the theta is completely unimportant. What I'm interested in is that. So I need, this is integrable, or exists, if and only if 2t minus 1 is greater than, less than, sorry, 1, right? So the threshold is 1. So we give a name to this thing, and you might think, well, that's something like the, you know, it's obviously a threshold, and you might think, well, call it some, you know, locally integrable threshold, but I'm going to call it the log canonical threshold. So this threshold is called the log canonical threshold. Of f, or actually, strictly speaking, better, what I'm really interested in is the zero locus of f equals 0. Okay, so let me do, let's see. So you can do one more example. Let me do one more example. Let's do a slightly more non-trivial example. Let's do C2 to C. So now I'm going to look at the function. So do something ever so slightly confusing. I'm now going to think of x and y as my coordinates in C2. They're not the real and the imaginary parts anymore, of course. And I'm going to sort of send that to y squared plus x cubed. And again, I can do the same thing. I can look at the integral over now dx dy, but of course this is, well, just look at, just ask the question, is when is 1 over y squared plus x cubed absolute value 2t integrable? And now the answer will be that the threshold is t equals 5,6 is the threshold. So, I mean, one way to do this is just to just straight do it. I mean, just straight try and compute the integral. It gets a bit tricky. You have to introduce polar coordinates, but you can do it with a bit of work. I didn't do it, to be honest, to be absolutely honest with you, but you'll get the answer t equals 5,6. So there's a much better way of doing it than just actually straight doing the integral. But before I get to that, let me come back to this problem. So how do we solve this problem? So, well, actually, maybe I should just very quickly say, are there any questions about the stuff about the integrability? Is that okay? Okay, so let's go back to this problem. So how do we see that there's an upper bound for the orthomorphism group of a curve? Well, just take G to be the orthomorphism of this group. So this is a finite group. So there's naturally a map from C to C mod G, which is another curve, call that B. And then, of course, I can just write down Riemann-Hurwitz for this guy. So if I write it down one way, I can write it down as Kc is pi upper star K of B plus the ramification. And, of course, I know the ramification has the form some EQ, let's say, minus 1 times Q, some points of C. But the point is that since this map is equivariant, I can exploit that fact, and I can rewrite this formula. In other words, you know, if locally the picture here is that I see a node and it's a 6-sheeted cover, I mean, not node. If I see a ramification of order 2, then I mean, with all those for those 6 sheets, I must just see three points of index 2. So I can rewrite this formula. I can say that Kc is pi upper star Kb plus pi upper star So let's see if I can get this right. So I mean, basically, I can take a branch divisor. So now I can sum over all points P in B. There'll be the same numbers. Let me call them now the branching index RP minus 1. But the thing is that since pi is degree r, of course I've got the so since pi has a degree, I've just got to divide through by the order of branching. In other words, you know, here there'd just be 6 sheets, so I'm dividing by 2 for each of these points. In other words, I can write this in the form pi alpha star kb plus delta, where delta has a very, very special form. So let's swap some points in, yeah, P and B. Okay, so now let's see. So I can then just take the degrees. Of course, the disadvantage of trying to do this is it's going to clash, right? So I can just take degrees, and I can just say that 2g minus 2, that's the genus, where g is the genus of C, is the degree of the cover, D. So of course that's nothing more than the order of G, times 2h minus 2, that's the contribution from K of B, plus the contribution from delta, which is of the form sum I equals 1 to, let's say, K, Ri minus 1 over Ri. So if I want to maximize, so I fix G, and I want to maximize D. So maximizing D means I minimize this. So I want to minimize 2h minus 2 plus sum equals 1 to K, Ri minus 1 over Ri. And then I do nothing more than just experiment. So if I take h at least 2, this sum, whatever it is, so let me call this V, then V is at least 2. Doesn't even matter what the branch points look like. Clearly just this guy gives me an integer at least 2. If I take h equals 1, well, this thing is 0. So the point is that I mean, this is positive, so this has to be positive, whatever it is. So I have to get at least one ramification point, and the minimum contribution is at least a half. So V is at least a half. So the final possibility is that h is 0. The base curve is P1, and then of course I get this minus 2, and then I've got to add these points back in and somehow get something that's positive. And it turns out the best case is where you take something of index 2, something of index 3, and something of index, something of index 7. And then of course this is 1 over 42, and then you just plug that back in, and you get exactly what you want. You get that the degree is no more than 42 times 2g minus 2. Okay, so from the point of view of bounding the automorphism group of a curve, or even actually just an automorphism group of a variety of general type, what you've got to deal with are expressions of the form the canonical divisors plus some other divisor delta. The key thing is that the coefficients of delta lie in some very nice set. So the thing about these numbers r minus 1 or rp, they satisfy the ascending chain condition. So the key point is that the set of numbers r minus 1 over r, where r is a natural number, satisfies the ascending chain condition. Just meaning that there's, you know, I can't find an infinite sequence of these that decreases.
Look, you're writing down the opposite.
Oh yeah, it's a descending chain condition. Thank you. Okay, good. And once that's true, basically there has to be a bound of some sort or other. The only question is what is exactly the bound? And then of course the other thing that's interesting is that this guy is positive, it's ample. Okay, so that's so much for automorphism groups of curves. Oops. Finish this. That's good. So I've lost the little piece that attaches to the thing. Well, what's that? You charge, okay. How much? So I don't know what I'm supposed to do, right? So. Try it, please. Oh, there it is. I see. That didn't come off. I see. Okay, got it. It doesn't seem very secure, to be honest, but okay. Okay, so let's see. So let me go back to the integration problem. So we had the function y squared plus x cubed, and I want to know what is this integrable. So the trick is to actually think about the curve, call this C, sitting of course inside C2 with coordinates x and y, of course. It's a curve with a cusp, and instead of doing the integral on C2, let's do the integral on the blow up, which resolves C. So of course we all know what to do. You take the cusp, you blow up, oh, okay, you blow up once and you get something that's tangent, gives you E1. You blow up another time, you're going to get three curves, I guess. You're going to get C tilde, let's call that 1, or C1, C2, E1, E2, and then of course finally you blow up and you get everything normal crossings. And then the observation is that the integral here was kind of tricky. The integral here is rather easy because everything's normal crossings, and you can just use so now everything's reduced to the case of something like locally something of the form x to the a y to the b, and to integrate that you can, or the reciprocal rate square it, you just need to use Fabini. So the only thing that's sort of tricky is that, of course, when you pass from here to here, you've just got to worry about changing coordinates, which is essentially what that means is keeping track of the canonical divisor. So what you've got to look at, let's call this S, is you've got to compare Ks plus C. So let's call this map pi. Guess I'm getting E1, E2, E3, pi alpha star Ks plus C, of course. So I put in this parameter T, and then I get Ks tilde, let's say, plus CT C3, I'm writing it, plus a bunch of numbers, E1, 2, E3, and then this guy, so the log canonical, so here, so f 1 over f to 2t is integrable. Well, the point is that you just have to keep track of these numbers. If any of these numbers becomes at least 1, then that's like saying you've just got locally something like z equals 0, and of course we've already seen that that's not integrable. So you just want the largest t such that a1, a2, a3 is less than or equal to 1. And you do the computation and you get 5, 6. So, and let me just tell you for free that the component which is coefficient 1 is E3. So there's a much quicker way of doing this calculation. So on this picture, so we got S tilde mapping to S. So the trick is, on this picture, let's contract both of these tails, the E1 and the E2. So then we get down to the picture, let me call it T, I suppose. So now I have an exception divisor E, which just corresponds to this guy. I've got two singular points, an A1 singularity, well, index 2, index 3. So this, of course, is all the way around. This is the -3 curve, this is the -2 curve. When you contract the -3 curve, you get a singularity which is a quotient singularity index 3. When you contract the -2 curve, you get a quotient singularity index 2. And of course, the C tilde just still passes through the same point. And now you just do a junction. So now you just say kt, k of t plus t of C3, or t of C tilde, excuse me, plus E. So the whole point is that this guy comes with coefficient 1. So the threshold is when one of these numbers is 1. The one that's 1 corresponds to E, and you can restrict to E and do a junction. So of course, classically you just get k of E, but there's a contribution from the singular points. So let's call this point Q, let's call this point P. So they contribute 1/2 P plus 2/3 Q. That's again just a local computation. And of course then there's a contribution from C, which is just straight transversal intersection. So that just becomes, I can just call this R, TR. So again, just take degrees. I get -2 plus 1/2 plus 2/3 plus t is supposed to be equal to 0. So t is equal to 5, 6. So that's a very quick way to calculate the log canonical threshold in that case. And the nice thing about that is it obviously generalizes. So for example, if you had x to the a plus y to the b, if you chose those numbers judiciously, then you'll get the same picture. You'll get one curve that contributes to the log canonical threshold. When you go to a log resolution, you get a whole bunch of exception divisors. There's one curve that corresponds to the log canonical threshold, that the guy that goes to 1. You'll get two singular points, one of index A, one of index B, and of course C will hopefully intersect the guy transversely. Actually, typically it will intersect with higher multiplicity. So then you're going to get something of the form A minus 1 over A plus B minus 1 over B, the contribution from those two singular points, the -2 from the copy of P1, and then of course, well, T, as I say, there could be some tangency in general. Could intersect in more than one point, or it could be tangent, or just intersecting more than one point, so T times K. So you're going to get something of the form T is 1 over K. Oh, bloody hell. I guess it's 1 over A plus 1 over B, right? Actually, you know what, I mean, I think actually the intersection is always transverse.
Depending on whether you've got A and B co-prime.
Yeah, okay. So let me just say that A and B are co-prime, thanks. So I suppose A and B are co-prime. I mean, it always comes down to the same computation, but let's get this. So more generally, if you took x to the A1 plus x2 to the A2 plus dot 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 x to n AN, you can do the same computation and you'll get something like this. Okay, so if you start looking at these numbers, they're obviously extremely special, and they satisfy a somewhat similar property to these numbers, although it's the other way around. So based on that, Shakurov made a conjecture that these numbers always satisfy ACC. So if you think about it, I mean, the only sort of thing you can do with in dimension n is increase some of these numbers, but if you increase these numbers, of course, then the fractions are getting smaller. And in fact, for hypersurfaces, this is now a theorem. So let me just state that. So this theorem can be attributed to, I mean, different parts were proved by different people, so let me just shorten the story by saying it's due to De Ferney, Ein, and Mustatsa. So I can actually even get the accents right. There we go. So you look at a set. So you fix the dimension n, and you look at all the real numbers, which are of course always rational, that you get as log canonical thresholds. Well, so you could express it in terms of some holomorphic function, or you could just take the zero locus, which is some hypersurface inside Cn. So look at that set, and then the point is that that set satisfies the ascending chain condition. And as I say, some very special cases, if you take something, polynomials which are very, very special, you can explicitly calculate what the log canonical threshold is, and lo and behold, those numbers satisfy ACC.
So you could define what log canonical threshold is?
I could indeed. Yeah, okay, yeah, right, yes, yeah, so, okay, so yeah, so yeah, okay, so it's just so I just want to think about what sort of generality I want to define this in. So yeah, okay, so definition, X be a normal variety let delta be a Q divisor such that kx plus delta is Q Cartier. So here, of course, the underlying variety is smooth, so there's no problem about something being Q Cartier. It just says the coefficients are rational. In general, that's going to be an issue. So let pi from y to x be a log resolution. So that means that it maps birational, and it means that y and the strict transform of delta and the exceptional locus, all of that is normal crossings. So then I can write, well, I can pull back kx plus delta, and I can compare that with ky plus the strict transform of delta, call that delta tilde, and then I'll get some extra stuff, which is I'll call E, and I'll write that. So say actually, let me write it differently. So I mean, I can write it that way, but let me write it this way. Let me just combine delta tilde and E. Let me call that gamma. So we say x delta is log canonical if sorry, we say this guy is KLT if the round down of gamma is less than or equal to 0. In other words, every coefficient of gamma is strictly less than 1. So log canonical is the limiting example of that. So that's where you allow some of the coefficients of gamma to be 1. So the log canonical threshold. So if delta is Q Cartier, then of course the point is if delta is Q Cartier, then kx plus T delta is Q Cartier. So then the log canonical threshold is the supremum of rho T, such that kx plus T delta is KLT. And again, in practice, that number will always be rational because you fix once and for all the log resolution, and you're only asking, you only look at finitely many exceptional divisors, and you only ask which, you only look at the components, which one is coefficient 1.
Excuse me, so for hypersurfaces in CN, this always ends up the same as its local integrability criterion?
Yes, absolutely, yes. I mean, it's connected to, it's the reciprocal of the Arnold multiplicity. It's to do with variation of Hodge structures. It's actually, these numbers are actually quite subtle and very interesting.
Log term is equivalent
L2,
to
yeah, exactly. But of course, in an arbitrary normal variety, it's kind of hard to talk about integrable. You need to go to some sort of resolution. Okay, so the first thing I want to say is that so Shakurov showed that these two notions are the two problems. The first one, the problem about the automorphism, bounding the automorphism group of a curve of general type, or in general of a variety of general type, and this problem, the problem about determining the log canonical threshold, they're actually very closely related for exactly the reason I pointed out before when I computed the log canonical threshold of the cusp. The point is that what you can do is you can go to some model, extract the divisor of coefficient 1, restrict to that guy, and get something which is numerically trivial. So Shakurov, clever observation is that the following, that the ACC, the log canonical threshold, follows from the following. So fix a set I coefficients. So the set I I'm going to think of as being a set of coefficients, and I want it to satisfy DCC. And again, hopefully you agree now that that's a reasonable condition. Then satisfying DCC, and fix, of course, n the dimension. Then so consider pairs x delta such that, well, let's say this guy is KLT and numerically trivial. So that's exactly what pops up when you extract the divisor of log discrepancy 0, in other words, coefficient 1, and you restrict to that guy. Exactly the key thing is you get something in dimension n minus 1, which is KLT, well, actually, you might be not KLT, but essentially, I mean, you can always reduce to that case and numerically trivial. And then the point is that then if you have a sequence xi delta I, an infinite sequence, then the number of components of delta I is increasing. I mean, another way of saying it is that if you look at pairs x delta, which are KLT, and kx plus delta is numerically trivial, then you can't have the situation, you can't have an ascending sequence in the sense that either the coefficients keep increasing or the number of components keep increasing. Anyway, so in this talk, the issue about the number of components increasing is not going to be an issue. So, I mean, I'll talk about this a little bit later. Okay. And okay, so now let me talk about something which seems to be completely different, but hopefully you'll see at the end that there's a connection between the thing I'm going to talk about and this conjecture, which is again then related to ACCs for the log canonical threshold. Okay, so let me start off with the theorem that I proved with Christopher a couple of years ago, which is also proved by some other two other sets of people. So as I say, this is due to Tsuji and Takayama, and then it was proved by Christopher and I. So it says the following: so fix n, which is just going to be the dimension. So then there is a constant Rn, natural number, such that if x is a smooth projective variety of dimension n of general type, then the map associated to the linear, the map is associated to a multiple of k of x, where of course r is at least Rn, is birational. Okay, so just to give you an idea of what's going on, let's look at low values of n. Suppose I take dimension of n equals 1. So in other words, we're looking at curves. Then everybody knows that R1 is 3. So 3 times the canonical series gives you a map into projective space, which is actually an isomorphism, right? And we can also classify the exceptions, right? Basically, it's either hyperelliptic if it's, R1 equals 1 works unless it's hyperelliptic, and R1 equals 2 works unless it's genus 2. Okay, so otherwise, if the dimension is 2, then Bombieri proved that, the R2 equals 5 will work. If you take a surface of general type, then 5 times the canonical series always gives you a birational map. And again, it's kind of interesting to classify the what happens in the exceptions. And then quite recently, a very nice result indeed, dimension 3. Well, this is probably not optimal, but 126 will do. So this is, it sounds quite like a large number, but before that, I think people thought the number was going to be in the thousands.
When you said it's interesting to analyze what happens in the exceptions.
Yeah. Well, so you always need 5. If you take an arbitrary surface, 5 will work. But sometimes 4 works, and sometimes 3 works, and sometimes 2 works. So for curves, 1 equals works unless it's hyperelliptic. Yeah. So yeah, it's very interesting to look at the surfaces for which.
Is there some generic phenomena for surfaces that are similar to curves?
Sorry?
Genus 2 answer.
No, so for curves, as you said, most of the time 1 works, right?
Yes.
So is there some generic thing on that for surfaces?
Well, I don't know about generic, but I suppose 1, right?
Phi2k is birational except finite in many cases and genus 2.
Yeah. Yes, there are people in the audience who know much more about this story than I did. Okay, and then so this was proved by two Chen and Chen. So let me say just Chen squared. 2 Chens. 3 Chens. Oh, okay. Okay, so yes, and it's a very, very nice result. But presumably that number is not optimal, but it's probably less than 100. But we're not quite sure yet. Okay, so let me tell you a little bit how this result is proved, and it will then relate back to, which is what I think what interests me at the moment is that this. I'll show you a connection between this theorem and this stuff about ACC. Okay, so what I need to tell you about is a sketch of how to prove this theorem. So this goes back to the method of Anghern and Hsu. So you've got your variety X. It's a general type. So you look at the linear system M times Kx, where M is large. So in other words, what you're interested in is H0 of MKX. So this will be this measures the dimension of this projective space. Well, subtract 1, and then the point is that this is sufficient. By Riemann-Roch, of course, the only thing that's important is the leading term, and this will be quite large. And the point is you pick X in X general, and you pick a divisor in this linear system such that the multiplicity at X of B is greater than twice N. And then what that guarantees is that XB is not, well, it's not even log canonical, but certainly not KLT. So then you look at the log canonical threshold. So you go down to the log canonical threshold. So this is lambda's the log canonical threshold. I beg your pardon, Miles?
Oh, 2n.
2n, yeah. Yeah, so you go down to the log canonical threshold locally at x. And then the point is that if x is an isolated log canonical center, we win. Because there's this whole theory developed by Hsu of multiple ideal sheaves, and that says that you can lift sections from log canonical centers. So if the exceptional divisor, which computes is the guy of coefficient 1, the log discrepancy 0, if that maps to a point, then you can lift sections from the point, but a point has a very simple geometry, and you can always find a non-vanishing section at that point, and you can lift that, and you can lift that to a non-vanishing section on the whole of x. Well, that at least tells you the linear system you're interested in has lots of sections, and then if you pick 2 points, you can sort of play around with this. You can run with this. But there's a problem, and it's a major problem. The problem is that there might be a positive dimensional guy containing x, which is the log canonical center. So very roughly, what the problem would be is you focus attention on one point, and you try and make the multiplicity at that point very large. Well, what happens if the divisor b that you pick has large multiplicity in along a positive dimensional subvariety containing x, and not just at that point? I mean, it sounds ridiculous, but that is exactly the problem. So now you'd like to lift sections from V, and you want to cut down to the case where you get down to a point. So to solve this problem, you want two things. One, you want you want to sort of do induction, and you want to say that there's a divisor on V. Well, so this guy will be inside some now multiple of kx plus lambda b, restricted to V. Of course, by the way, it doesn't matter. I mean, working with kx plus lambda b doesn't bother us, because this is just a multiple of the original linear system we were interested in. Whoops. So that's okay. And again, this guy will be large. But that's going to be okay as long as the multiplicity of b0 prime is very large. And then the other thing we want to do is we want to lift b0 prime to b0 on x, and then that will cut down the dimension of our log canonical center. So I'm going to focus on this problem. And I'm essentially, this is not an easy step either, but let me just focus on one. So what do you want? I mean, you want to find something of high multiplicity. So you want a large, for m large, you want this to be large. So let's just measure what that is. Let's just give a name to that. So definition, so that x is, let's say, a normal variety. Actually, let's just say normal variety. D a divisor. So then the volume of D, let's write it, vol of D. Well, it's just how fast that linear system grows. So I can just take the limit as m goes to infinity. Well, I want to normalize, of course. So I divide through by m to the n. And then actually just if you think about Riemann Roch, I want to divide through by n factorial as well. So the point is that if D was a, if D was an ample divisor, that would just be the leading term in Riemann Roch. So then if you say what Anghon Hsu actually proved, they proved translate what they proved to this kind of language. They proved if D is a divisor on a smooth variety such that the volume of D restricted to every subvariety is sufficiently large, and they gave explicit constants to say exactly what sufficiently large means, though they're not particularly nice constants, then that implies that Kx plus D is birational. I mean, defines a birational map. Because I mean, ignoring this issue, basically it just says they can keep going. They restrict to V. They have something. They want to again concentrate the log, find a divisor log of high multiplicity, and they kind of lift that, and they just keep going. Okay, so let me make a sneaky observation. It sounds, this observation is going to be seems kind of silly, but it's going to be, hopefully it's going to be the key to.
Sorry, does the sufficiently large depend on the variety?
I beg your pardon?
So it depends on the variety.
They're sufficiently large? Yeah. No, it's just, these numbers are just, they're like 2 to the n or something, but no, they're independent. Yeah. Sorry?
I'm sorry, what did you say?
I mean, they're sort of exponential in dimension, but they're constant. Yeah, I mean, yeah, that's the whole point. I mean, yeah. Yeah, I mean, they used it to prove a version of Fujita's conjecture. Okay, so let me make just one sneaky observation. So suppose D is, so D gives you a birational map. So D birational is a slightly sloppy way of saying things, but I just want to say that the map, the linear system given by D is birational. The sneaky observation is you kind of think about what's going on here. This tells you that Kx plus 2n times D is birational. Actually, maybe I want to say 2n plus 1. So the point is, it's the same sort of trick. If D is birational, then essentially at a point, on an open set, it acts like an ample divisor. So you can just sort of take the intersection of n guys, create a log canonical center at a point. You can do that at 2 different points, completely free. That's why you need 2n, and then the plus 1 just says there's a little bit, you can extract a little bit positivity left over, and you can run these arguments.
So that means 2n plus 1d are not k plus 2. What's the terminology?
I beg your pardon?
Do you mean they're 2n plus 1d is birational, or k?
Well, if D is birational, any multiple of D is birational. Just the linear. All I mean is just that, given any divisor, I get a map to projective space. But what I'm saying is, if D is birational, then in the linear system 2ND, in the linear system ND, if I pick a general point of X, I can create an isolated log canonical center. While 2n says I can do it at 2 different points. And then the plus 1 says I have a little bit of positivity left over to apply something like Karl-Martin Wigner vanishing. And I can use the method of Anghon Hsu to, just at 2 different points, find separations that separate those 2 different points. Just by lifting, Okay, you have to use multiple ideal sheaves, which just says that you can lift sections from points. But if you can lift sections from points and you've got 2 different points, essentially it almost tells you something birational. Okay, so.
H1 of the restricted map is not
I beg your pardon?
When you lift a section, you lift a section without vanishing of H1. Something.
Sure. Yeah, but you need some. I mean, you need a multiply sheet with some positivity. So, I mean, I use the +1 as the actual explicit constants aren't so important. It's just that it's something independent of n. Okay, so how am I going to use this? So let me start off by stating conjecture. Conjecture A, just so I can write down a theorem involving the conjecture A. So fix 0, 1 a DC set. For example, you know, R minus 1 over R. And then again, fix the dimension. So the conjecture is that you can find a number m. Yeah, okay, m. Such that if x delta is log smooth, log canonical, well, let's say coefficients of delta belong to I. So let me just point out one minor thing. It seems kind of silly, but one of the big advantages of working with the volume is you don't have to work on the minimal model. You don't have to work on you don't require D to be net. So I can sort of all these statements become a lot easier. I can just require everything to be log smooth if I just work with the volume. But anyway, so of course I want kx plus delta to be big. That's like general type. And here's the sort of sneaky thing. I say there's some integer. This guy is Cartier. Well, x is smooth, so that all that's meaning is I'm just clearing denominators. So if all this stuff is true, then I want to say then so I clear denominators, so I get Cartier divisor. Some fixed multiple of that gives me a birational map. So I want to finish off by sort of showing you that this implies Shakurov's conjecture. So you might have forgotten what Shakurov's conjecture is, but let me just sort of say exactly what that means I have to prove. So suppose not, then there exists xi delta I. The number of components of delta I is fixed such that, well, kx plus I plus delta I is KLT, numerically trivial, and the coefficients of delta I are increasing. Of course, they're bounded above by 1, so they're increasing. So the point is that they approach a limit. So they approach a limit. Let me call that A1 up to AN. So I want to say one other thing. We can also reduce to the case that kx plus 1 minus epsilon delta I, this guy is Fano, is ample. So, I mean, I just sort of run some sort of MMP. I get to, I mean, you know, by some sort of induction, I somehow reduce to the case where I want a Mori fiber space, do induction on the dimension of the fiber, reduce the case that say it's even say Picard number 1, and then this is actually kind of easy to show that. Then if I decrease the coefficients ever so slightly or decrease them to 0, I get something which is ample. I'm on a Fano variety.
We're writing 1 minus epsilon.
Yeah, well, so I could even say it's ample.
Depends on I.
No, just, I mean, the guy is numerically trivial, so I decrease it by any amount.
Oh, I see.
So then you see, what that tells me, if I increase delta I get something general type. So let delta I prime, so if I mean, these are, I mean, I order the components of each delta I, and they each tend to a limit. So let delta I prime be the same as delta I, but with coefficients, you know, a1 up to an. So I match up the components, I just increase them to the limit. So what I know is that kxi plus delta I prime is ample. In particular, it's of general type. You know, it's big. I guess I'm cheating a little bit here, but the point is, you know, if I want to go back to log smooth, I can just say it's big. Okay, so in the interest of time, let me just cheat a little bit. Let's suppose that these limiting coefficients were rational. Then I'd know that some fixed multiple of this, oh I see, I should have said, oh no, that's okay. So I know that some fixed multiple of this guy gives me a birational map. So I know that m times r kxi plus delta I prime is birational. I pick my m. I apply this, I know that kx plus mr kxi plus delta I prime is birational. In particular, it's big. But you see, I can rewrite this as kxi, well, to do the algebra, right? So mr, oh, there's 2n, right? Sorry guys. 2nmr plus 1, well, that's what's in front of kxi, so let me pull that out. Then there's a 2nmr, and then that's divided by 2nmr plus 1. So whatever this number is, it's slightly less than 1. So this guy is birational. I need this kind of annoying thing about here. In the general case, of course, I'll need to increase the delta I prime a little bit more than delta I, apply Diophantine approximation, and say that I can get very, very close to delta I prime, have the denominators of the rational guys very small, and run a similar argument. Okay, thank you very much.